And here we are. It is another physics video lecture. Physics 190 video lecture 7. A lot of great stuff today. So we're doing contour integration. We've learned about Cauchy's theorem, Cauchy's integral formula, and what we ended with last time was just an amazing thing. So we're doing contour integrals, and what we discovered was we could take an integral f of x dx, say defined on the entire real axis, and we could interpret it as a complex function, or just extend it into the complex plane, and then this integral around this path is 0. So the integral we're looking for is this one, and that's the limit as r goes to infinity. So there's our real integral. The entire integral vanishes if you take it around the complex plane. And if there's a pole here, and I'll just take the one that we found here around I, then this entire integral, or the one along the real axis, turns out to just be the evaluation of the integrand at the pole. Okay. Leaving out some steps, and it was based on the idea that this contour went here and around there clockwise and back, so forth. Okay, so we did some of these contour integrals that allowed us to almost magically just pick off the integration, and we're going to keep doing that, but we want to extend it to a greater class of integrals. Right now, in order to have this semicircular contour, in order to have its integral vanish, we needed to have a sufficiently strong power in the denominator. Okay, so we needed dz over z to the, we had z squared, we definitely have to have z to the 1 plus something. I'll just write 1 plus alpha. And that covers a number of functions that we integrate, but by no means all the ones that we want to integrate. So we need a stronger theorem or lemma called Jordan's lemma that will allow us to extend the class of functions so we can do these integrations. Okay. So again, what we were doing was this integral here, I'll just designate it like that. F of z dz, it's self-vanishing, okay, as r goes to infinity. Okay, so we have something called Jordan's lemma. That's an interesting tool, and it's going to state the following. Jordan's lemma so let C sub r be equal to r e to the I theta 0 less or equal to theta less or equal to pi. So that's that semicircular path that we're talking about up there. Then the integral along C sub r of e to the iz dz. It's going to bring a whole new class of functions if we can use this e to the iz here. So this integral in the limit as r goes to infinity is less than pi. Yes. Less than pi. And that's going to be really good because this is bounded, and therefore pretty much any function in here that vanishes as r goes to infinity will be amenable to these approximations here, to these estimates. So that's Jordan's lemma. We're integrating around this path right here, just the top half, the semicircle, and we're looking for an estimate for e to the iz. Now what we're gonna realize is, we're used to e to the I theta or e to the ix, which is always just bounded by 1. However, e to the iz takes on different values as we go up here to the upper half plane. So good, let's leave this right here and then prove that lemma. And we immediately get a couple of interesting applications off of it. Okay, so this is the integral that we're looking at. E to the iz dz along this contour. And we're going to estimate it. So that's less than or equal to integral e to the iz dz when we take the absolute values inside the integral sign. Okay. So now let's look at what this is. We're looking at the absolute value of e to the iz. Hold on, the dz there. Yeah. So let's go ahead and write down what we have here. E to the iz is equal to e to the I cosine r cos theta plus I r sine theta, right? That's our z, so plug that in there. The dz is equal to I r e to the I theta d theta. Okay, so we've been here before. Let's go ahead and write it all in there though. E to the I r cos theta plus I r sine theta. And then we can put that there. And now for the dz, absolute value again, I r e to the I theta d theta. So what's going to happen here, since we're doing absolute values, that's our c sub r. Okay, we're doing absolute values. You can see I e to the I theta is just going to be a 1. I'll just underline those. I e to the I theta is going to be 1. So we're just going to be left with r d theta. And here e to the I r cos theta is also going to have absolute value of 1. So this simplifies to still over c. Actually, we can now state the boundaries. It's going to be 0 to pi e to the minus r sine theta, and then we're going to have an r d theta. So this is the integral we have to estimate. We want to take r goes to infinity. We get a divergence here, but we get something getting smaller there. We're going to have to do a little clever estimate on this thing. And that is the following. You can see this geometrically. You've got 1 here and pi over 2 right there. Then the sine comes up like that. On the other hand, the straight line that goes from the origin to there is always less than or equal to the sine. So what we have is sine of theta is always less than or equal to 1 divided by pi over 2. Okay. Make sure I'm not missing anything. Yeah. Oh, other way around. Good thing I got that. So sine of theta is greater than equal to this straight line, and this straight line is just theta divided by pi over 2, rise over the run, right? Theta axis over pi over 2. So there's the substitution we can make in here. So this is less than or equal to 0 to pi. I've got r, I've got e to the minus theta divided by pi over 2, or I could say 2 theta r over pi, and then d theta. Okay. And at this point, this integral is easy to do. So, we'll go up here and look at this. Use the right half of the board. So, equals r e to the minus 2r over pi theta. Theta r divided by 2r over pi minus sine e to the minus 2r theta over pi, 0 to pi. These cancel, equals pi times one minus, get rid of that minus sign, e to the minus 2r. Good. And in the limit as r goes to infinity, we just have pi. So it goes to pi as r goes to infinity. So there's our estimate. And that, like I said, is a lot stronger than the Darboux estimate that we would have had. And we can immediately put this to use. Okay. So yeah, make sure you have all of this in nice form and order. And I want to kind of do a corollary to this, and then I'll give you guys a nice integral to figure out. So let's see, making sure we have everything here. You know what, I think I have an error up here. Let's see what I was thinking. Ah, yes, I did. Okay, let's correct this while we have a chance. So my limit was going to be from 0 to pi over 2. So I actually had pi over 2 here's the pi. So here I had a 2 factor of 2 and take it from 0 to pi over 2. Okay. I'm probably going to change my substitution a little bit. So we've got 2r but we're actually 2r is going to work out. That was right. So we have 2r, 2's canceled. We have the pi and pi over 2 e to the minus r. Okay, that does it. If it doesn't, you guys clean it up. Okay, so now let's leave that there. And we'll use this side of the board. So the first thing I want you guys to do is, let's just call this a corollary. Namely, we had this path here for integral e to the iz dz, right? What if we have e to the minus iz? What about integral e to the minus iz dz? Question mark. So if we want to do the estimate of this integral here, what we're going to find is, see, I still have that up there. If we had minus iz, we would have plus r sine theta. So that estimate would go wrong, okay? This would be fine, but the minus I right there, the cosine would be fine, but the minus I times I would be positive r sine theta. So how do we deal with that? And the answer is, we have to go around here. So we have to investigate the integral, taking the integral in the path in the lower half plane. And that's something you have to be aware of, because later on when we're doing these integrals, sometimes we have to complete the contour in the lower half plane as opposed to the upper half plane. So I'll just put here for homework, but this is the kind of thing, leave a big space in your notes. You know, everything we're doing could actually be incorporated into the notes, even the homework problems, but leave the space in your notes to show this. Namely, that we complete the path in the lower half complex plane. And that'll be a nice chance to review what we had up here. Okay. So this is good. And the homework problem I want to assign now and I'll even formulate it as a show that. So homework, show that integral 0 to infinity cosine ax over 1 plus x squared dx, that's a worthy integral, is equal to pi over 2 e to the minus absolute value of a. Anything else to be said about that one? It's a good one. Yeah. Okay, so this is a great one to do the estimate on, do the calculation. You can see the pole is going to be, 1 plus, x plus I, x minus I, like we did the other day. Since you were asking 0 to infinity, you can just multiply, take the minus infinity to infinity plus infinity, and then you're taking half of that. You also see that when a is equal to 0, you got 1 over 1 plus x squared. That's just the pi value that we found the other day. And yeah, this will be an application of using this thing here. As far as the absolute value goes, if you analyze this just from the standpoint of a real integral, you can see that because the cosine is an even function, it doesn't matter if a is positive or negative. Okay. So that essentially allows you to declare this absolute value sign valid already. Yeah, and then there's a couple of ways to do this. You can say, well, my cosine is the real part of, well, of this type of expression here. Or, yeah, cosine AX is the real part of your e to the IAX, or z. Or you could express the cosine as the sum of the two exponential functions. But if you do that, you're going to have to split your integrals up and do one in the lower half plane, one in the upper half plane. Good, so however you decide to do this one, it's a pretty rich problem to think about. And I think I'll leave it at that. Yeah. Okay, let's see where that takes us. Discussion of the lower and upper half plane. That's good. Let's see how we're doing time-wise. Okay, very good. So what's next here? We're going to go back to Cauchy's integral formula. By the way, this is the type of thing that's going to come up in our physics applications. In fact, all of these examples are going to take a real physical turn later on. Right now, we're just amazed at the kind of integrals we can do. So we have to extend the theory a fair way so that we can do everything we want. So I'm going to go back to the integral formula and we'll continue the analysis there. We eventually want to have Taylor series at our disposal, and then we'll generalize those as well. So we're back to the Cauchy integral formula. And I'm going to write it this way. F of z is equal to 1 over 2 pi I integral closed path f of zeta d zeta. Okay. We'll make our zeta look good. Good Greek letter in place of z, and then zeta minus z. So that way I don't have the subscript on the z right now, right? This was before it was f of z naught, now it's f of z, and there's our integration variable zeta. And just to when z is inside the contour C and it's 0 when z is exterior to the contour. Okay. So now we're going to use this thing. Oh, I need one other formula. Where is that in my concept? I'll get that going right away. So this is the first thing we're going to use. Second thing is a well-known series that sum over z to the n equals 0 to infinity is equal to 1 over 1 minus z. So we need a proof of this for complex numbers before we take Taylor series, because we don't have the Taylor expansion yet. Okay. So there's a kind of an algebraic way to prove this, and let's see what our best way at that is. Yeah, one can do it with induction. Well, let me write down what I did right here, and then we'll see. Because we just want to prove it algebraically, and then take this limit n goes to infinity. Yeah, so here's what I have. I have z sum over z to the n equals 0 to capital N minus sum over z to the n plus 1 n equals 0 to capital N equals 1 minus z sum over z to the n equals 0 to capital N. Good. On the other hand, this side here is just 1 minus z to the n plus 1. Okay, just look at the difference of all the terms in here. Okay, this is a finite sum, this one starts with 1. This one ends with z to the capital N plus 1. So that's what I have there. Equals 1 minus z n equals 0 to n z to the n. Okay, so that's just an arithmetic fact. And I'll continue down here. Just a fact, so sum over z to the n equals 0, capital N is equal to 1 minus z to the n plus 1 divided by 1 minus z. And now we just want to take the limit n goes to infinity. Now let z be less than 1 in magnitude. It's a complex number now. Less than 1 in magnitude, then z to the n is equal to r to the n e to the I n theta, right? For some theta somewhere inside the unit circle. So this r to the n, since the magnitude here is less than 1, this r is strictly less than 1. And if you take the, let's call this capital N, by the way, since that's what we've got, that's what we're working with, capital N. So if you take n to infinity, this r to the n goes to 0 uniformly. Okay. And that's why if we take n here to infinity, we're going to get a number, complex number whose magnitude goes to 0 as n goes to infinity, and we're left with what's right up there. And limit z to the n magnitude is equal to the limit r to the n goes to infinity, and that clearly goes to 0. Okay, so that leaves us with that series up there that's so important and useful. So yeah, this was the proof. So we have, that is the one ingredient, and this is what we're going to work with. So the first step, I'm numbering things, right? So the first thing we want to do is take the derivative of f of z. In this form here. Okay. So the derivative of f of z, we'll just construct the difference quotient. So f of z plus delta z minus f of z divided by delta z. There's a difference quotient. When we've gotten far enough with this thing, we'll take the limit as this delta z goes to 0. But right now we're working with that integral, so that's 1 over 2 pi I, whatever our contour is. So we're looking at f of zeta d zeta, right? The z plus delta z comes from here, so we have 1 over zeta minus z plus delta z minus, running out of room here, we've got our proof already, minus 1 over z minus zeta. Zeta minus z, yeah. Okay. And I must have a delta z in here somewhere. I'll put it right here for now. Now let's simplify this expression. We've got 1 over 2 pi I integral f of zeta d zeta. There's our delta z. And this, we have zeta minus z minus zeta minus z. So that cancels, and we just end up with the delta z. Okay. So minus delta z minus plus. So we end up with a delta z. That's going to be the cancellation. And we take the limit, and we're left with, in the denominator, zeta minus z plus delta z times zeta minus z. So this expression is great. We want to take that limit. These are gone, no difficulties left. We can just take the limit of delta z in here. And so we get, and I'll just continue the equal signs here. We're all right. Limit as delta z goes to 0, we're left with 1 over 2 pi I integral f of zeta d zeta, zeta minus z, the quantity squared. Okay. So it's as though we had just differentiated right under the integral sign. Okay. That's all that happened there. So this is equal to f prime of z. Okay. There's f of z, this is f prime of z. Now that we've done it, we see we could have just differentiated with respect to z under the integral sign. All would have been well. And now, since we've done it once, we could just repeat this exercise again, and each time we're going to get another power here, and then factor of 2, and then factor of 3, and so forth. So this generalizes immediately, and we've found, I'll put it in a box here, the nth derivative of z, of f of z, so the nth derivative, 1 over 2 pi I, and yeah, there's going to be that n factorial, so n factorial 2 pi I integral f of zeta d zeta, zeta minus z, flows contour along wherever that path is. So good, we have the nth derivative. By induction. From this one right here. Okay. Let's see. Okay, I'm going to start the next construction. I want to make use of this in our eye now, and now we want to do the Taylor series. I'm not going to complete this right now. I'm going to set it up though. So for the Taylor series, we want to have this f of z using this formula, okay, f of zeta d zeta minus z. We have to pay attention to the domain of integration now. So expand about z sub 0. So this next sketch is pretty important. Okay. And what we'll do is we'll have concentric circles. So here's our z sub 0. And by the way, here we were discussing radii of convergence. So this is germane. So we've got a z sub 0. We draw two concentric circles here. And our zeta is on the outer circle. Okay, so when we're doing integral d zeta, we're talking about the outer circle, and on the inner circle here is where my z is. Okay. So these are concentric circles. And what we're going to make use of is that this zeta minus z is by construction greater than z minus z0. Actually, zeta minus z0 is greater than z minus z0. So this is on the outer circle, z is on the inner circle. Outer circle, z is on the inner circle, which means that zeta minus z naught is always going to be greater than z minus z naught, and this is how we're going to do our expansion. Okay, should we just do that now? That's the question. Now I'm going to save it for next time. Okay, because we've done a bit. So go ahead and review all this stuff. I'll tell you what we're going to do. It won't be that hard. We're going to plug in this expansion here. I'm going to find it in this expression and just continue this thing into a Taylor series. So it's actually a really nice construction. Just want to make sure we have enough time for it. Anything else? No, I think we're good. So we're just practicing using the Cauchy integral formula, whose utility we've already come to appreciate. And this is the construction we're going to put on the board next time. In fact, I'm going to have to put this on the board next time, this whole board, and then work our way down. Okay, good. See you guys next time.